Just 1 second.
Okay, are you ready?
Sí, amor, estoy con el micrófono. Okay, I'm ready.
Okay. Good afternoon and welcome to the European Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Pablo Zadunaisky from the University of Buenos Aires. The title of his talk is Clebsch-Gordan Revisited. Please, Pablo.
Thank you very much, and thank you for the invitation. Oh, sorry, I'm getting some background noise from my tablet. Give me just a second, please. I'm going to try to shut it down. Yeah, that should do it. Yeah, perfect. Apology. Okay, so as just mentioned, the title of my talk is I never know how to write Clebsch-Gordan Revisited. But so it's been a while since we arranged for this talk, and I've sort of changed a little bit my perspective towards this. So let me change a little bit the name of the talk. I want to call it Peary's Rule Revisited. And if you don't know what Peary's Rule is, I will tell you in just a second. So this is joint work in progress with Joanna Meinel from the University of Bonn. And it's about some very old, very classical stuff relating the finite dimensional representation theory of the Lie algebra GLN. So my talk will have 3 parts. So first, I will go through some basics of rep theory of the Lie algebra GLN. In particular, I will talk about this Peary rule, which says how you decompose a certain tensor product of 2 representations. And by some general theory, in each one of these simple representations you will find, there will be something called the highest weight vector. And these guys exist by theory, but I want to find them explicitly. So the meat of the result is related to finding highest weight vectors in GLN reps. And finally, if time allows, I will discuss some variations on that theme. Okay, so let's review the representation theory of GLN relevant for the talk. By the way, please, if anything is unclear, just interrupt me. The point of the whole talk is that I will try to be extremely concrete about the objects I will find. There's a lot of abstract theory behind this, and the whole point is that I want to make some very concrete constructions behind. Okay, so I will just introduce some notation. Sorry, I have a message here. Yeah, okay. Nothing. Okay, so I will just write down G for the Lie algebra of n by n complex matrices, where n will be some natural number. I would denote by B, it's Borel algebra, which just means that I will be taking upper triangular matrices. This will be called the Borel. It will be denoted by B. I will denote by H, what is usually called the Cartan subalgebra, just diagonal subalgebra with zeros outside. And there will be something called the positive nilpotent part, which is contained in the Borel. And this is just, you take strictly upper symmetric matrices. So inside this Lie algebra, I want to distinguish three families of elements, which will be called EI, HI, and FI. EI is an elementary matrix that is just above the diagonal, right? So it looks like this. So there's zeros in the diagonal, and there's a 1 just above the diagonal. That's the EI. The FI will be the transpose of an EI, so the 1 will be just below. And the HI will be the commutator of these two, which is just a diagonal matrix with a 1 and a -1 right next to the other. So it's 0, and then there's a 1, a -1, and then the rest are zeros. Okay, so what does the representation theory of this Lie algebra look like? Well, I'm looking essentially for finite dimensional vector spaces where I can find matrices that satisfy all the commutation relations that these three matrices satisfy. So the really interesting, well, usually one looks at the representation theory of SLN instead of GLN because SLN is semi-simple, while GLN has some non-semi-simple finite dimensional representation, but those are really small and one can safely ignore them. So if you're more familiar with SLN representation theory, just remember that GLN behaves essentially the same way. So in particular, I want to talk about the irreducible representations of my Lie algebra G. So what do they look like? Well, they are classified by a guy that lives in the dual of the Cartan subalgebra. This guy will be written as a direct sum of as a sum of epsilon I. These are just the functionals that take a diagonal matrix and return the entry in the ith diagonal position. And so for each one of these guys, you will have an irreducible representation if and only if the difference between two consecutive coefficients is a positive integer. So let me remind you quickly how this works. If you take a finite dimensional reducible representation of GLN, it decomposes as a direct sum of what's called weight spaces. Apologies for the noise coming outside if you're hearing that. So what is this? This is just a vector space formed by those vectors in here, such that any element in the diagonal acts diagonally. This is just an eigenvector, and the eigenvalue is just the lambda I. Okay, so if you make a drawing inside the vector space H star of the eigenvectors, so the simultaneous eigenvectors that you find here, you find out two things. First, it's invariant by the action of the symmetric group. The symmetric group permutes all this weight. So you will find a very symmetric picture like this. And among all the weights that satisfy these conditions here, you will see that only a few fall inside this region here. I think my tablet stopped transmitting. I think. Let me try again. Okay. So as I was draw the news that appear inside this vector space. So the weight that will appear inside the vector space, you will picture. And a few of those weights will fall inside the region defined by these equations right here. And among those, there will be one that will be furthest away from zero. That guy is called the highest weight. Highest weight. And it's the one that identifies this L. So out of this L, you know that by general theory, there will be exactly one irreducible representation of GLN that will have this lambda in particular as the highest weight, and that recovers the representation you started with. And so in particular, one thing that one should notice is that if you look at the highest weight component, so if you look at all vectors whose weight is given by the lambda that is also giving you the highest weight, it will be spanned by a single vector. This weight component is one-dimensional. So we can talk about the highest weight vector is well defined up to scalars. Okay, so let me give you some examples of this. So if you look for a representation whose highest weight is precisely the element in the dual vector space of the Cartan that just returns the first of the entries in a diagonal matrix, well, you just get the natural representation of GLN acting on this vector spaces matrix. And in fact, this of course has a basis. There will be the canonical basis of C to the N will give you a basis of weight spaces. So the weights that will be present in this representation are just epsilon1, epsilon2, and so on up to epsilon n, which of course is, as I said, it's invariant by the action of the symmetric group. And each one of these vectors has this, the obvious weight, right? The weight that I've added as a subset. A second example is that if you take the algebra itself and you act on it by the adjoint action, then the Cartan is just the zero weight component. And then there's a bunch of one-dimensional weight components, which are just the sum of the elementary matrix. Each one of these guys is of weight epsilon I minus epsilon j. So in fact, if you look at it, well, this guy is not going to be simple. It's semi-simple because in here, there is inside the zero weight component, there is an element that commutes with everyone. That's the identity. And then there's going to be another highest weight. So there's one vector which is highest weight of weight 0, and there's another vector which is of highest weight epsilon 1 minus epsilon n. And so this is not a simple representation, but it's semi-simple. And this is how it decomposes. And most representations of finite dimensional representations will decompose like this. In particular, if the Lie algebra H, if the Cartan subalgebra acts diagonally on the representation, that will guarantee that this just looks like a representation of SLN, and in particular, it is semi-simple. One thing I forgot to say is that this highest weight vector is easy between inverted commas to identify. It's it spans precisely the space of all vectors that are killed by the upper triangular subalgebra, the strictly upper triangle. Okay, so this is a brief review of what the representation theory of GLN in finite dimension is. And I want to add one more thing. I want to mention what Piery's rule. So Piery's rule will tell you how to look at this representation. Turns out that if you take the tensor product of two finite dimensional simple representations, then it will be again semi-simple. This is completely general. But in particular, Piery's rule is telling you how to decompose this particular tensor product. So remember that this is just the natural representation seen as a representation of GLN. Okay, so how does this decompose? It decomposes as a direct sum of simple representations. So I have to tell you what their highest weights are going to be, and they're going to be related to lambda, and you're going to get lambda plus one of these epsilon I guys. But this sum is not over all epsilon I, because it might just happen that lambda plus epsilon I does not satisfy this condition. Right, this one, the one that tells you that what a highest weight looks like. But that's the only restriction. So Piery's rule says that this sum is over all epsilon I such that lambda plus epsilon I satisfies this condition, right? That condition is called dominant. So this is whenever one of these weights is dominant, this will appear in the decomposition of this tensor product. So Piery's rule plus some theory is telling you that inside this tensor product, there is you should expect to find some n highest weight vectors, right? N, the same n as in GLN. So this should work in general, and then in some special cases, it will fail. But if you take lambda generic enough, then there should be n different highest weight vectors in this tensor product. So the problem is to find them all. By find them, I mean choose some basis in the tensor product and write down the highest weight vectors in this basis. Preferably, take a basis from L lambda, a basis from L epsilon 1. The basis from L epsilon 1, we already know which one we're going to take. And produce a basis in the tensor product and just tell me what the highest weight vectors will be in terms of this bigger base. And this problem was solved for n equal to 2. The first problem is to choose the basis that you're going to look for, and then to find the coefficients of the highest weight vectors in this basis. This problem was solved for n equal to 2. For n equal to, these are the Clebsch-Gordan coefficients. And as far as I know, there are some, well, this is completely solved. It's been known for a long, long time. As far as I know, there are some results for n larger than or equal to 3 when you take some nice bases. And well, depending on which basis you choose for L lambda, the problem is more or less solved, as long as you don't care too much about what the basis originally is. So if you take the canonical basis, this problem is relatively easy to solve in some sense. The canonical basis coming from quantum groups and all. The little problem is that we cannot actually compute canonical basis except in very small examples. So there's still room to be more explicit in solving this problem. So I want to talk about now about finding the highest weight vectors. Before I go on, are there any questions? Okay. What I want to find is highest weight vectors of weight lambda plus epsilon k inside this tensor product. And the first observation one should do is that these vectors are going to have weight lambda plus epsilon k. So this guy is going to look like this. It's going to be some lambda 1 tensor v epsilon 1 plus w2 tensor v epsilon 2 and so on. wn tensor v epsilon n. And since this tensor product has to have weight lambda plus epsilon k, just a little computation tells you that this guy has to have weight lambda plus epsilon k minus epsilon 1. This w has to have weight lambda plus epsilon k minus epsilon 2, and so on. So a couple of very easy examples. The only possible choice for the highest weight vector of weight lambda plus epsilon 1 is v lambda tensor v epsilon 1. This is the only choice. This is forced. You don't even have to think about it. You can try thinking a bit harder about where you're going to look for a highest weight vector of weight lambda plus epsilon 2. And you'd like to just take, I'm just going to take this vector. And that's not really a good idea because unlike in the first case, this is not the only vector you're going to find of this weight. It's not hard because this is the other weight of the corresponding weight. Remember this element F1, you just have to take the V lambda as by F1, and then this guy will have weight lambda plus epsilon 2 minus epsilon 1. So this elementary tensor has the correct weight, and these two vectors span the component of weight lambda plus epsilon 2. So if you know by Pierre's rule that there has to be some vector, some highest weight vector of weight lambda plus epsilon 2, you know that it has to be some linear combination of these two guys, and you work for a while and you find that this is the correct linear combination. So that's not that hard. You can do it by hand. And if you try to do the same for lambda plus epsilon 3, it gets worse and worse and worse as you go down the list. But this this second example should set the tone for what's going to happen next. So in general, if you look at this writing here, if you think of this guy as having this form, there are several simple observations you can make. For example, if you go all the way to the end, this element, this last element, has a weight that is impossible, that you cannot find inside the original, this guy. This has a weight that you're not going to find in the original vector space. So you can delete it. In fact, you can delete all the terms up to WK, epsilon K. So you know it's going to be a smaller linear combination. It's only going to involve the first K vectors inside the natural representation. And when you try to, well, something else you want to check is, well, when is this true? Right? You want this guy to be a highest weight vector. You want it to be annihilated by all upper triangular matrices. And out of this, you get a very nice condition, which essentially says that if you compute this, what you get is this linear combination. So just acting on the first component of the tensor, plus only one extra term, which comes from the action on the second tensor. And this implies that if this is going to be a highest weight vector, then the Wi's have to satisfy the following equations. You have to get R plus 1 has to just come from the WR, and the ERs have to kill all the other WRs. So rearranging all of this, what this means is that in this linear combination, the only guy you need to find is the W1, because applying E1, you're going to get the W2 minus W2. You need to apply this. And then by applying minus E2, you're going to get W3 and so on. So it turns out that it all depends on finding this W1, which from this condition here has to be a highest weight vector for the subalgebra spanned by E2, E3, E4, and etc. So the point is that this is all determined by a vector W1, which is of weight lambda minus epsilon 1 plus epsilon k, and highest weight vector for the Lie subalgebra of matrices of n minus 1 by n minus 1 matrices stuck in the lower right corner. I want to stop for a second here and mention that this was relatively surprising, because usually when you restrict the action of GLN to a certain GLN minus 1 subalgebra, this is quite standard and it's been known, and you know that it doesn't really depend on which copy of GLN minus 1 you find, as long as it contains a chunk of the cartan, of the original cartan. But basically, probably just for standard psychological reasons, I've always found people choose the upper right, upper left corner subalgebra. So it took us a while to process that we were working with the lower right corner. But it turns out that, yeah, you need to do that. And quite surprisingly, what this is saying is that you need to think of L epsilon 1 as, well, I will try to return to this later on. I don't want to get bogged up into too much philosophy, but this was a detail that took a while to gel in our heads. it was surprisingly a stumbling block for us at some point. Okay. All I have to do now is to construct a highest weight vector inside the L lambda representation. So it reduces to everything reduces to finding this lambda one, which is found in the original L lambda representation. Okay. So here's a result that was already known quite a while ago. There is some element inside the enveloping algebra of the negative part of the negative nilpotent of this weight, and it needs to be tweaked by some element in the enveloping algebra of the Cartan, such that the following happens. If you apply this to the highest weight vector V lambda, then you get this highest weight vector that you are looking for, if it exists, and zero otherwise. And the point I want to stress is that this element is independent of lambda. So this is a sort of universal constructor of highest weight vectors for for smaller leaves of algebras of the algebra you're working with. There are formulas for these guys. In fact, more general results are known. These are known as lowering operators in the literature, but they go by many names. So you probably, if you've seen them, maybe you've seen them with a different name. They have several avatars. And this is the part where people usually compute with the upper left corner GLN -1 instead of the lower right corner. So it took us a long time to just translate all the formulas and make them work. In the end, we didn't do that. We found our own path to this formula, to this guy. And it's lucky that we did, because we made some nice discoveries along the way. So let me tell you something about our proof of the existence of this guy. I'm not claiming it. I want to insist, I'm not claiming any originality in the proof that this guy exists. It's been known for a long time. It's, let's see, I think even in the 70s, it was known. It's part of one of the many proofs of the existence of the Gell-Van-Zeppelin basis and its formulas for GLN representations. So these guys have been known for a while. And there are even explicit formulas, etc. I just want to tell you how we find them. And to find them, we use an observation, which is that you can find a nice basis of this chunk of the enveloping algebra. So this is just one particular weight component of the enveloping algebra of the negative part. So it's a monomial in the F, and it's parametrized by something, which is just a sequence of arrows moving up or down. So it's either an up or down arrow. We can talk about what this means later. I don't want to go into too many details. It's important that this is a parameter set. And this basis has a nice property. So if you act on the highest weight vector of your representation, it may or may not be zero. But if you pull out the zero in this list, then this is a basis of L lambda, which is the place where we are looking for our highest weight vector. And this is quite remarkable, right? This is a basis that, when applied to a highest weight vector, remains a basis as long as you take out the ones that act by zero. This is not standard at all. Usually you find bases that, when you act on the highest weight vector, well, some new relations appear among the bases. You have to throw away a few, and maybe you have some nice control on which ones you have to keep and which ones you have to throw away. But the fact that if you stick with the non-zero ones, then you get a basis, that's very special. That's the behavior you expect from the canonical basis. And that, well, that's not really common. Basically what's going on is that this little guy, this set, gives you the canonical basis in this small weight component. It's a weight component that's not really deep into the algebra, so it's not strange that you can find it explicitly, but still, we've never seen it written down before. So there's that. And so if our pk, our element pk, if it exists, then it's going to be a linear combination of this form. So it's some of this monomial and some accompanying polynomials in the generators of the Lie algebra. And this is the part where we take a guess. We take a jump. My colleague is German, so I should say we take an ansatz. And we assume that this can be written down as follows. Remember that this theta is just a list of arrows, up or down, up or down, up or down. And we're going to assume that this splits as a product of polynomials, each depending on each arrow independently. And it turns out that if you impose what you want on this sequence, so you want pk to produce some highest weight vector, then you get a recurrence that settles who these polynomials have to be. So the first polynomial, the one right here, if your first arrow is an upwards arrow, then this has to be the element hk minus 1 plus 1. So remember, this is just some, this guy is epsilon k, ek minus 1, k minus 1 minus ek, seen as an element in the enveloping algebra. While if down out, this guy has to be minus hk minus 1. That's the starting point of the recurrence, and then you end up with the following recurrence rule. So I'm going to write it down as a matrix because I find it quite impressive that this is what happens. So did you lose?
Okay, I think that the recording is okay now. Jabir, can you confirm, please? Okay, please go on.
Okay.
Okay.
So there's this remarkable recurrence. Notice that this is a matrix in the enveloping algebra of the Cartan of the Lie algebra. And one pretty surprising fact is that this matrix you can try to diagonalize it. It's not diagonalizable, but the recurrence turns out to be quite nice. It's a sort of Fibonacci recurrence inside the Cartans of algebra, and this completely determines the polynomials that you want to find, and this is how you find the pk. So this gives the element. So essentially, we write down some very explicit elements and we just go looking for them. And while the final formula is quite demanding to actually spell out, it does produce explicit elements. And I will show you some by the end of the talk. Now, as a corollary, we get the following result. It comes immediately from the previous one. there is an element inside this tensor product. So the tensor product of the negative Borel, the enveloping algebra of the negative Borel tensor, the enveloping algebra of the negative nilpotent part, such that the following happens. If you start with the obvious highest weight vector inside this tensor product, and you act on it by this element, then it is going to produce the highest weight vector I am looking for. So this is either the highest weight vector of weight, there you go. No, sorry. No epsilon. This guy, if it exists, and zero otherwise. And the way you prove this is that this the process of getting, I'm going to be a bit quicker here, but the process of going from the pk to the theta k is completely analogous to the way we started with the W1 and then produced the all other WK vectors, right? Remember, this was just minus something. You start with W1 and then you apply E1 and then E2 and so on. And so this is how you get an element that looks quite complicated. Let me just write down what the general formula looks like without giving too much detail. This is going to be a sum of guys of this form. So there's going, again, there's this up, down arrow sequences. Some monomials, and then two types of polynomials on the H's. Ones that depend on the sequence. There are modified versions of the previous ones. And another one that does not depend on the sequence H, tensor some sequence of F. So I start with Fi. I want to start with F1, F2, Fi. And this chunk, this right-hand chunk, just comes from the fact that this is how you successively construct the vectors inside the natural representation. You take the highest weight vector and then you apply F1, which turns it into the second vector in the canonical basis. Then F2 will turn it into the third vector, and F3, and so on. The other part, it just comes from applying this process to the analogous portion of the pk element to turn it into a theta k. And again, while a bit complicated, you can really compute this out. These are some polynomials that obey some complicated recurrence relations, but it takes surprisingly short time to actually compute them. Okay, so I want to stress that these guys are completely independent of the highest weight we started with. They may or may not produce highest weight vectors, but whenever there's a highest weight vector, they will produce. So I like to think of this as sort of universal witnesses of the fact that Pieri's rule holds. Pieri's rule is completely regular, it's in a sense independent of the lambda, because there is something living in a place that doesn't depend on lambda at all, that will act by producing whatever Pieri's rule promises it will produce. Such an idea, I found out only rather recently, goes back to a paper by Roger Howie in the 80s. It's Roger Howie and someone else. I apologize, I can't remember the name of the second author, but I can remember the title of the paper, which is called why the Littlewood-Richardson rule should be true. The Peary rule is just a special case of the Littlewood-Richardson rule. And he essentially says that such elements, such universal elements should exist. And he goes and finds them somewhere else, not in the enveloping algebra of the Lie algebra, but in some other operator algebra somewhere else, which are probably the same elements, just seen in a different place through some different map. But this idea that some universal witness to the Peary rule should exist, it apparently has a lot of history. This is something I only recently found out. Okay, so how are we doing on time? Do I have 10 more minutes? Thank you. Yes,
Yes, you have
is the other
10 minutes.
Very well, thank you. Apologies for forgetting about the second author there. Okay, so I want to just point out a couple of extra variations on this idea. So I'm going to be very quick about this. First, you can quantize all of this. You can quantize this. And it all works out. There is a quantum Peary rule, which says exactly the same, and there are quantum Peary elements. And surprisingly, you have to go through the proof again to find the quantum Peary element. And there's a point where you get to this same recurrence here. And as usual, quantization makes the situation much more rigid. And this matrix becomes diagonalizable with eigenvalues q and q minus 1, which means that there are two families of quantum Peary elements. In the non-quantum case, in the classical case, there was only one. In the quantum case, you have two. You can exchange q and q minus 1, q and minus q minus 1, which essentially reduces. We think we've reduced it to the fact that you can work with type 1 or non-type 1 representations, and then the Peary rule gets a little skewed. But essentially, you can do the same computations. It gets a lot harder, and the polynomials are a lot more complicated, but they also get organized more nicely because, as usual, the extra rigidity forces you to organize things a bit more. But I also want to point out the second one, which is that you can generalize the previous result, the following theorem. If you have any representation of the enveloping algebra, finite or infinite dimensional, it doesn't matter. And you have a highest weight vector in here of weight lambda, then by general theory, V tensor, the natural representation, will contain a highest weight vector of weight V lambda epsilon K, sometimes not. Again, the Peary rule tells you sometimes you will get one, sometimes you won't. But it will always be given by this guy. So you can use only finite dimensional representations to find this universal witness to Peary's rule, but you can use it to construct highest weight vectors on infinite dimensional representation. Things work just the same. And here's where I want to show you an example. I didn't manage to check the image, but I had it open and it closed. Let's see if I can find it quickly. Yeah, here it is. These are the highest weight vectors that you find by tensoring M0, the Verma module of highest weight 0, with the natural representation L epsilon 1, at least for GL3. I did not mention this, but this the construction is completely compatible with enlarging GLN onto GLN plus 1. So this, in fact, gives you all the highest weight vectors of this weight inside M0 tensor, the natural representation for arbitrary GLN for n larger than 3. So I didn't manage to take this, but so let me explain what we're looking at here. We're looking at a double entry table where the first column is showing you the highest weight vectors inside the Verma module M0, right? So you have one of weight V0, one of weight epsilon 2 minus epsilon 1, minus epsilon 2 minus epsilon 3, and so on. So that's the first column you're seeing. The second column, the first row is showing you the explicit form of the corresponding highest weight vector when you tensor V lambda with the highest weight vector V epsilon 1 or V epsilon 2, or the linear combination, or this is the linear combination you have to find to produce the highest weight vector in the tensor product. So for example, I cannot write on top of this, but in the, say, 1, 1 box, you find V0 tensor V epsilon 1, which is the obvious highest weight vector inside this tensor product. And down that column, what you find is just vectors of the form, well, the highest weight vectors inside M0, tensor V epsilon 1. And that gives you a bunch of highest weight vectors inside that tensor product. In the second column, you get the highest weight vectors that you get from the slightly more complicated construction, the one that I showed that you can do just by considering some simple linear combination. Okay, you get a few. The formulas are a bit more complicated. At the bottom, in parentheses, you can see what the weights of these highest weight vectors are, and you can hear my 2-year-old in the background screaming. So these guys are a bit more complicated, but okay, you can still produce them essentially by hand. In the third column, you find the highest weight vectors that come out from the action of theta 3, the big guy that's producing this extra highest weight vectors. And here, the formulas get truly complicated. This thing you see in the top row is the universal formula for a highest weight vector of weight lambda plus epsilon 3. And here you get several new guys. And what we can prove is that this will be all the highest weight vectors inside the tensor product. So this produces all highest weight vectors inside the tensor product of a Verma with this particular finite dimensional representation. There will be some repetitions. If you look at the boxes that are closed with the same color, they will be the same. You get the same vector. There will be repetitions because essentially there's not enough room in the tensor product to get different highest weight vectors with the same highest weight. But these are, we know by theory that these are all the highest weight vectors that we should get. But this is a very abstract construction. Once you have the Pierre elements in your hand, you can find all of these tensor products. So this is the level of explicitness that we were aiming for. We were just not we just weren't thinking about infinite dimensional representations when we started. It just turned out that these guys also do the work inside an infinite dimensional representation. And I think that's my time. So thank you very much for your attention. Oops. I want to stop sharing.
Okay. Thank you very much, Pablo, for your interesting talk. Are there any questions? Or comments or remarks? Yes, there is a question on the chat.
Yes, So the last part about infinite dimensional representation. So maybe I can write down something about this. Just a sec. Let me share screen again. So what's going on is this. In the example I showed, I looked at the Verma module M0, and I tensored it with the representation L epsilon 1. And by general theory, it is known that this decomposes as a direct sum of this Verma module. So each of these guys is a highest weight vector of infinite dimension. General theory also tells you that there will be a highest weight vector here of weight v epsilon 1, and that there will be 5 more. If you draw them, they will look like this hexagon. I suck at drawing hexagons, so I will probably, yeah. So there will be 5 other highest weight vectors, and these are the ones that appear in the first column of my of the little table I showed you. Sorry, not on the first column. They appear mixed up in between. You have to go looking for which ones are at each place. In here and in here, there will be a highest weight vector of weight v epsilon 2 and v epsilon 3, but here you will only get 2 extra highest weight vectors. But the formulas that we produce invariably produce 6 highest weight vectors for each one of these Verma modules, which means that there will be repetition. And the point is that this, and if I remember correctly, this and this will appear twice in the table. And you can, using some abstract theory, predict which ones have to appear twice when you compute this. But the main point, no, I'm sorry, I'm confusing this. No. It's this. It's all of these guys that appear twice. So the ones coming from M epsilon 1 will appear only once, but all the other guys will appear twice on the list. Essentially, because sometimes they will appear by the action of some theta 1, and sometimes they will appear by the action of some theta 2 or theta 3, but you can construct them in several different ways. But you will always get the same vector. And it's quite surprising that you don't even get different multiples of them. You get the same vector. That's probably also explainable, but it's a fact. So the point is that this element, this theta k, though constructed solely by looking at the finite dimensional representation theory of the Lie algebra, can still I mean, they are hard workers. They can go to the infinite dimensional world and still do their job in there. Thank you.
Okay. Thank you. Any other question? Okay, I cannot see any questions. So in this case, let's thank the speaker again. And,
thank you so much.
You're welcome. We will resume on next Monday at the usual time. Thank you very much. Bye-bye.
Thank you for the invitation. Bye-bye.
Bye.